Welcome to Introduction to Significant Figures. This video is part of a series in Foundations of Engineering by Conceptual Calculus. Math often uses exact values. For example, a circle with radius r has an area of exactly pi r squared. In this equation, pi is not 3.14. It is 3.14159265358979 and more. The decimal representation of pi continues infinitely, never ending or repeating. This exactness is an abstract concept, not a physical object. Engineering involves physical objects. Engineering relies on measurements of those physical objects, which are never exact. We can't cut a board exactly pi feet long. In engineering, pi equals 3.14 is often close enough. Measuring my driveway. If I stretch a bit, my stride is a yard long. I paced my driveway and found that it is 31 strides long. So my driveway is about 31 yards long. What is that in meters? We take the 31 yards and multiply by a conversion factor of 0.9144 meters per yard to get a result of 28.3464 meters. Is my driveway really 28.3464 meters long? That 4 on the end represents 4/10,000ths of a meter, which is 4/10ths of a millimeter. Do I really know the length of my driveway to a fraction of a millimeter just from pacing it? Of course not. Do not claim more than you know. You might think 28.3464 meters is more accurate than 28 meters. It is less accurate. All those decimal places tell your reader that you know the value to a fraction of a millimeter, when you do not. That is not accurate. A digit is significant if it conveys real information. When I say my driveway is 28 meters long, that is accurate information from my measurement, so the 2 and the 8 are significant. Saying my driveway is 28.3464 meters long claims accuracy that my measurement does not provide, so I should not say that. We use significant figures to clearly express the information we have and to understand someone else when they express the information they have. Engineers need significant figures for accurate technical communication. In the next few minutes, we will learn to identify the number of significant figures in a given value. In a later video, we will learn how to determine the number of significant figures to use when reporting the result of a calculation. Here are some basic rules for significant figures. Any digit other than 0 is always significant. 23.456 has 5 significant figures. 0 is significant if it occurs between other digits. 9001 has 4 significant figures. Zeros to the right of the decimal. Leading zeros are not significant. 0.00025 has 2 significant figures, the 2 and the 5. Zeros to the right of the decimal point are significant only if they follow other digits. 0.004 has 1 significant figure, the 4. 0.00400 has 3 significant figures, the 4 and the 2 zeros that come after it. A value given as 2,000 meters with a decimal point after the 2,000 was measured to the nearest meter. It has 4 significant figures. What about 2,000 meters without the decimal point? Maybe it was measured to the nearest meter and just happened to come out to a round number. Maybe it was measured to the nearest 10, 100, or 1,000 meters. Without more information, we cannot rely on more than one significant figure. If we put our 2,000-meter measurement into scientific notation, then we can make its precision clear. 2 times 10 to the third power has 1 significant figure. It was measured to the nearest 1,000 meters. 2.0 times 10 to the third power meters has 2 significant figures. It was measured to the nearest 100 meters. 2.00 times 10 to the third power meters has 3 significant figures. It was measured to the nearest 10 meters. 2.000 times 10 to the third power meters has 4 significant figures. It was measured to the nearest meter. Significant figures are not the same as decimal places. The number of decimal places includes only digits to the right of the decimal point, and it includes all of them, whether they are significant or not. For example, 123.0450 has 7 significant figures and 4 decimal places. 0.000160 has 3 significant figures and 6 decimal places. Now you try some. Pause the video, complete the chart, and then restart the video to see how you did. Welcome back. In the first row, 2,960 has a decimal point but no digits after it. Because there are no digits to the right of the decimal point, it has 0 decimal places. The decimal point tells us that all the digits to its left are significant, so there are 4 significant figures. The second row also has 2,960, but without the decimal point. Again, there are no decimal places, but what about the significant figures? Certainly the 2, 9, and 6 are significant. Maybe this was measured to the nearest 10 units. Or maybe it was measured to the nearest 1 unit and happened to be a round number. Whoever wrote this did not make that clear. We can't rely on the 0 to be the result of a precise measurement, so we call this 3 significant figures. If we want to know more about it, we will have to ask the person who took the measurement. The number on the third row has 5 decimal places and 7 significant figures. The fourth row also has 5 decimal places, but only 3 significant figures because leading zeros are not significant. Finally, on the bottom row, we have a number in scientific notation. This makes the number of significant figures perfectly clear. There are 2. It does leave one wondering what to say about decimal places. As it is written here, we see 1 digit to the right of the decimal point, so 1 decimal place. However, this number could also be written as 2,000, which has no decimal places. To the best of my ability to determine, there is no universal agreement on which to use. I would accept either 0 or 1 as a correct answer. My driveway measurement was not precise enough to provide any real information about millimeters or even centimeters, so those digits are not significant. I want to use only digits that are backed by real information from my measurement. To do this, I round the number. Let's take a quick look at how to do that. To round a number, first decide how many significant figures you want. In the driveway example, I want 2 significant figures. Then, look at the next digit to the right. If it is 4 or less, round down. If it is 5 or greater, round up. In this example, that digit is 3, so we round down to 28 meters. Now you try some. Pause the video, round each number to the requested number of significant figures, and then restart the video to see how you did. Welcome back. On the first row, we want 2 significant figures, so we look at the third digit from the left. It is a 3, so we round down, leaving the 120 unchanged. Next, we want 4 significant figures, so we look at the 5th digit. It is a 7, so we round up. The 0 in the thousandths place becomes a 1. On the third row, we want 3 significant figures, so we look at the 4th digit. It is a 0, so we leave the digits to the left unchanged. Finally, we want 4 significant figures, so we look at the 5th digit. It is a 9, so we round up. To the left of it is also a 9. Rounding that up gives 10, so we have a 0 in that place and carry a 1 over to the left. There we add it to another 9, putting a 0 in that place and carrying the 1 further to the left. We end up with 200.0. I hope this has been helpful. Conceptual Calculus thanks VIVA, Virginia's Academic Library Consortium, and New River Community College for their generous support.